how you communicate across different media. So from water to air interface will be the first paper. The second one will be from inside the body to outside the body, so from deep tissue to outside. And then the second half of papers that you'll see in the session are on communication in sort of new emerging environments and deployments. So backscatter across long-range wireless links but at low power. And the final one will be on sort of communication from high-speed trains. So you'll also see a lot of different technologies here, millimeter wave and backscatter and LTE. So for those of you who are unfamiliar in wireless, you'll get a good introduction to the space of different technologies as well. So with that, let me introduce the first speaker. This first speaker is Junsu Zhang, sorry. Hi. Okay, who's a first-year graduate student at MIT working with Father Ladib. And he's going to be talking about networking across boundaries, communication through the water-air interface.
One, thank you very much, Deepak, for the introduction, and thank you all for coming here today. I'm Junsu Zhang from MIT, and I'm very excited to be here today to tell you about our research on networking across boundaries, specifically about enabling wireless communication through water-air interface. I'm presenting this work on behalf of the authors, my colleagues Francesco and Fado, who unfortunately could not present today. So, let me start by asking you a question. Did you know that a deeply submerged submarine cannot communicate with an airplane? So the submarine that you see over here cannot communicate with the airplane that's above the surface. In fact, any deeply submerged underwater nodes, like the underwater sensors or vehicles, cannot communicate with the nodes above the surface of the water. You might be wondering why. Well, the reason is that wireless signals work well only in a single medium. So for example, it can work well either in the air or in the water, but it cannot work well across both. So for example, a submarine can communicate with another submarine using an acoustic signal or sonar. In the air, mobile phones can communicate with phone towers using radio signals, like the cellular or Wi-Fi. However, neither of these work well in the other medium. So a simple question that one might ask is, well, why can't we simply transmit an acoustic signal to communicate directly with the node above the surface? Well, the reason is that if you were to transmit an acoustic signal from underwater to the water surface, it's going to reflect back, and you will not be able to cross the boundary. So why not transmit radio signals? This is because radio signals die in water. So it's not even going to be able to reach the surface. In fact, this is the reason that we use acoustic signals underwater in the first place. So how do people overcome this problem today? One approach is to use a relay node, and let me tell you what I mean by that. A relay node is partially submerged underwater, and it has an acoustic transceiver in the water and an antenna in the air. So for example, if a submarine wishes to communicate with a radio tower, it's going to transmit an acoustic signal, which gets received by the relay node. And the relay node is going to re-emit this signal as a radio wave in the air. However, the problem with this approach is that these relay nodes can easily drift away with waves, which cuts the communication link. Furthermore, you cannot furnish the entire ocean surface with these relay nodes. So another approach is to have these underwater vehicles to surface to a depth at which you can effectively communicate using radio signals. However, it will take forever for an underwater drone to go up and down and up and down. It will be a very time-consuming and expensive procedure. So today, there is still no effective approach for an underwater node to communicate with the node above the surface. And in this talk, I'll be telling you about the first technology that enables wireless communication across water-air interface. Now, we're not going to enable a submarine to communicate with an airplane, but we will enable an underwater sensor to communicate with the sensor above the surface. And here's the idea. We're going to use an underwater speaker, which transmits an acoustic signal, and the signal is going to travel as a pressure wave. And when the pressure wave hits the surface, it's going to cause a tiny vibration on the surface. To measure this tiny vibration, we're going to use a radar. This radar transmits a radio signal which reflects off the surface and comes back. The radar is going to use this reflected signal to measure the surface vibration. So if an underwater speaker transmits a different signal, it's going to change the surface vibration, whose change is now detected by the radar. And this is how we can enable an underwater node to communicate across water-air interface. Effectively, what we have done is to transform the water surface from an obstacle itself into communication medium. And this allows us to achieve the best of the both worlds, RF in the air and acoustic on the water. And in this talk, I'll be telling you about this technology. And we call this translational acoustic RF communication, or TARF, because it enables communication by using the translation from acoustic to RF. So it is the first technology that enables wireless communication across water-air interface. Theoretically, it achieves the best of the both RF in the air and acoustic in the water. I will also show you how we can deal with practical challenges like the natural surface waves. And finally, I will show you how we implemented and tested our system under practical scenarios. And before I go into details, let me tell you how this technology paves the way to future applications. So the first application is, which I've already told you about, is submarine to airplane communication. The second application is finding airplanes that go missing underwater. In the past years, we have seen cases when these airplanes go missing underwater, and it was very difficult to find them. And if the future airplanes were equipped with this technology, it can help us in finding these airplanes when they go missing underwater. The last application is ocean scientific exploration. Today, a majority of ocean still remains unexplored. And this is because it is very difficult to deploy underwater sensors and communicate with them. And with this technology, we can deploy an array of wireless underwater sensors that can communicate directly with the nodes above the surface. And with this, let us now go back to the key idea underlying this technology. So the key idea was that we're going to use an underwater speaker that transmits an acoustic signal, which hits the surface, causing a surface vibration. And we're going to use a sensitive radar to measure the surface vibration. So the first question that one might ask is, well, can we sense the surface vibration? Can we sense the surface vibration that was caused by the transmitted underwater acoustic signal? To answer this question, we ran an experiment by transmitting an acoustic signal at 100 hertz. Over here, we used the underwater speaker to transmit a signal, and we measured the surface vibration. And over here, what I'm going to do is to plot the surface vibration. On the x-axis, I have time, and on the y-axis, I have the displacement. And when we transmit a signal at 100 hertz, this is the vibration that we get. And as you can see, the displacement is varying with 100 hertz. But what's more interesting is that this vibration has an amplitude of 10 micrometer. This is a very tiny signal. So how can we sense such microscale vibration? Remember that I told you that we were going to use a radar to measure the surface vibration. However, to measure micrometer vibration, it's going to require hundreds of terahertz of bandwidth, and this is 1 million times larger than the bandwidth of today's state-of-the-art Wi-Fi or LTE devices. Not only is this impractical and costly, there's simply nothing like this that exists today. So how can we overcome this problem? To overcome this problem, what we're going to do is instead measure the changes in the displacement using the angle of the millimeter wave radar. So the radio signal travels as a wave, and this wave is going to have an angle. And when there's any changes in the displacement of the surface, it's going to change the angle. So when the pressure wave hits the surface, causing a tiny vibration on the surface, this vibration is going to lead to a change in the angle of the millimeter wave radar. And this angle can be expressed as 360 degrees times displacement over wavelength. This is nice because with a wavelength of 5 millimeter and a displacement amplitude of 10 micrometer, we now get an angle variation at 7.2 degrees, which is now detectable using our sensor. So now, the angle of the millimeter wave encodes the transmitted information from underwater. So great. Now we have a way for us to sense a tiny vibration on the surface. So are we done? Well, not really, because there still remains one problem. And this problem is the natural surface waves. So for example, even on calm days, ocean surface ripples, also known as capillary waves, have amplitude of 2 centimeter peak to peak. This is already 1,000 times larger than the surface vibration caused by an acoustic signal. So how can we even sense the surface vibration even in the presence of even such a weak ocean ripples? Well, here's the idea. What we're going to do is to treat the natural surface waves as structured interference and filter it out. These naturally occurring surface waves are relatively slow, so their frequencies vary from 1 to 2 hertz. On the other hand, our transmitted signal operates from 100 hertz to 200 hertz. And since these signals are now separated in the frequency domain, we can use filtering. So for example, in the frequency domain, over here I have the frequency on the x-axis and the power on the y-axis. This is a representative signal that we get. The portion over here with the lower frequencies correspond to the natural surface waves, and the portion over here with the higher frequencies correspond to the transmitted signal. So a simple solution would be to use filtering to eliminate the impact of the natural surface waves and look into the signals from 100 hertz to 200 hertz. So we actually went ahead and tried it. But unfortunately, it did not work. So simply filtering out does not solve the problem, and here's the reason why. Previously, I told you that the angle is 360 degrees times displacement over wavelength. However, this was not the whole story. Actually, there was modulus 360 degrees, which means that the angle is going to wrap around every 360 degrees, and when I plot the surface displacement, it's going to look something like this. And over here, you can see that now it has an amplitude of 5 millimeter peak to peak, which is much larger than the surface vibration that we have seen previously. What you also notice is that the displacement is wrapping around at every 5 millimeter. And this is because of modulus 360 degrees. And this wrapping around is nonlinear, and therefore it corrupts our signal. And this is why simply filtering out alone does not solve the problem. But if there's a way for us to track this natural surface wave, then we may be able to eliminate its impact on our signal. And that's exactly what we do. And let me show you what happens. So here, we're going to track and unwrap the displacement wrapping. And with this, we get a trend that looks more like the water surface wave. And we now have an amplitude peak to peak of 2 centimeter, which corresponds to the capillary waves that I told you about. And the tiny vibration on top of it is the transmitted signal from our underwater speaker. So now, we can go ahead and filter out the impact of the natural water surface wave. And this is the signal that we get. On the x-axis, I plot the time, and on the displacement, I plot the displacement again. And we were now able to extract the original signal that was transmitted at 100 hertz. So by treating the natural surface wave as structured interference, we're now able to track and eliminate its impact on our signal. And this is how we can sense our tiny vibration even in the presence of natural surface waves. So how can we communicate using this new communication modality? How can we send bits of zeros and ones? And here's a very simple example. Let us say we want to transmit a bit of 0, then we can send at 100 hertz, the acoustic signal. This is going to cause a surface vibration at 100 hertz, causing the angle variation at 100 hertz. Alternatively, to send a bit of 1, we can transmit an acoustic signal at 200 hertz, which causes the surface vibration and angle variation at 200 hertz. So to send a sequence of bits of zeros and ones, we can send a signal at 100 hertz and 200 hertz. Of course, this is a very simplified example that borrows a technique called frequency shift keying. However, in this new communication modality, it has some unique properties. And the paper introduces an algorithm for optimal power allocation and rate adaptation for more effective water-to-air communication. To implement for the receiver, we built our own FMCW millimeter wave radar that operates with the center frequency of 60 gigahertz and the bandwidth of 3 gigahertz. And this radar acts as a daughter board to the USRP software radio. As for the transmitter, we use an electro-voice underwater loudspeaker that operates with the center frequency of 150 hertz and the bandwidth of 100 hertz. And we connect it to two different types of preamplifiers so that we can transmit using two different power transmission powers. And I want to note that this is considered to be relatively low power for underwater communication. We evaluate our systems in two different settings. For the controlled experiment, we use a water tank that you see over here. And as you can see, you see the acoustic transmitter and the radar. And to experiment at much larger depth and in less controlled environment, we performed our evaluation in a swimming pool, as well as in the presence of the swimmers. So in the pool, the swimmers and the current circulation were causing constant ripples on the surface. And as you can see, there are the acoustic transmitters and the radar receivers. So now, let me show you our throughput results. In this experiment, we vary the power and the depth of the underwater transmission. And over here, I'm going to plot the signal-to-noise ratio in decibel on the x-axis and the throughputs in bits per second on the y-axis. We also perform our evaluation using different modulation scheme. So in the case of using the BPSK, this is the result that we get. And as expected, with higher SNRs, we get higher throughputs. In the case of BPSK, which is the lowest modulation scheme, we get a throughput of 100 bits per second. We also used QPSK and 16 QAM, and as expected by using the higher modulation scheme, we're able to reach higher bits per second, or the throughput, at higher SNRs. And finally, this is the result of using the TARF's optimal rate adaptation. And as you can see, it generally outperforms the other modulation schemes. And I would also like to note that hundreds of bits per second is typical for underwater communication. And this shows that TARF is a valid communication technology and that it can adapt to different channels. Next, I want to show you our results for the signal-to-noise ratio versus depth. On the x-axis, I plot the depth in meters, and on the y-axis, I plot the signal-to-noise ratio in decibel. And this is the result that we get. And as expected, the SNR degrades with depth. In fact, it closely follows the theoretical trend of 1 over depth squared. And remember that we were transmitting at a much lower power for underwater communication. So in practice, underwater communication would allow us to use much higher power, allowing us to operate at larger depth. And finally, let me show you how the system is able to deal with different waves. In this experiment, we generated artificial waves of different peak-to-peak amplitudes. On the x-axis, I plot the wave height in centimeter, and on the y-axis, I plot the normalized throughput. So in the absence of waves, we get the normalized throughput of 1. And this is a result of the throughput in the case of wave with 2 centimeter peak-to-peak. And remember, this is similar to the capillary waves, which is dominant in ocean surface waves on calm days. We're still able to get a similar throughput compared to the case when we don't have any waves. We also stress tested our system to see how it performs in the presence of larger waves, and this is the result that we have. Notice that beyond 20 centimeter, we're no longer able to establish communication link. However, even with the presence of waves that are 16 centimeter peak-to-peak, we're able to achieve half of the normalized throughput. And this shows that TARF is able to operate in the presence of waves that are 1,000 times larger than the surface vibration itself. To conclude, I want to show you a quick video of our working setup. Here we have the underwater speaker and the radar, and the speaker transmits a signal which is received and decoded by our radar. And this allows an underwater node to communicate with the node that is above the surface. So, in this presentation, I have told you about TARF, Translational Acoustic RF Communication. TARF presents a new communication modality that enables wireless transmission across water-air interface. I also described to you a prototype system that demonstrates an uplink communication from underwater to the air, and that can deal with practical challenges like the natural surface waves.